Welcome to the TOEFL Listening section. In this part, you will hear one or more conversations in an academic or campus context, such as a discussion between a student and a professor, or between two students. You may take notes while listening. Listen to part of a conversation. You will hear it only once, so listen carefully. After the conversation, you will answer questions about what you heard. Some questions will ask you about main ideas and details. Others will ask about implied meaning, speaker attitude, or how ideas relate to one another. Use both what is stated and what is implied to answer.
Hi, Dr. Thompson. Thanks for meeting with me. During office hours, I wanted to go over my research plan on ice core climate records before I start analyzing the samples.
Of course, Maya. Pull up a chair. Tell me which cores you are focusing on, and what question you want to answer.
I am planning to compare atmospheric CO2 and methane records from several polar drilling projects to see how abrupt changes in greenhouse gases line up with temperature proxies. I was thinking of using Vostok Epica Dome, CGISP2, and Law Dome records.
That is a good selection. Each of those ice core records has different temporal resolution and different age ranges, which will matter for your comparisons.
Right. I read that Epica extends back about 800,000 years and Vostok about 400,000 years. Is that correct? Yes. Epica gave the longest continuous CO2 record.
Yes, Epica Dome C extended the CO2 record to roughly 800,000 years. Vostok covered about 420,000 years, and Law Dome gives very high resolution for the last 1,000 years or so.
Can we talk about how the gas measurements relate to the ice age? I am confused about the gas age-ice age difference. I keep seeing that phrase in papers.
Good question. The gas age-ice age difference is fundamental in ice core work. As snow compacts into firn and then into ice, the air is still connected to the atmosphere through the porous firn layer. The bubbles close off at a certain depth, called the lock-in zone. When bubbles close off, the trapped air is younger than the surrounding ice at that depth because the ice formed earlier than the final trapping of the gas.
So if I pick a depth, I cannot assume the gas and ice represent exactly the same year. I need to correct for that offset.
Exactly. The age difference depends on accumulation rate temperature and firn thickness. In high accumulation sites like Law Dome, the offset is small, sometimes a few years to decades. In low accumulation Antarctic cores like Epica, the offset can be centuries to millennia.
That explains why Law Dome is useful for recent high-resolution CO2 trends, including the industrial rise.
Yes, Law Dome provides annual to sub-annual resolution over the last 1 to 2,000 years and captures the sharp CO2 rise in the industrial era, which is helpful for calibrating instrumental records.
When you said calibrating, what methods do labs use to measure gas concentrations and isotopes in the cores?
There are a few standard approaches. For concentration measurements, labs often extract trapped air by mechanically crushing or melting ice in a vacuum, and then analyze the released gases with gas chromatographs and mass spectrometers. Isotopic ratios for water like δ¹⁸ or δD come from continuous flow systems and isotope ratio mass spectrometers.
And the isotopes are proxies for past temperature, right? δ¹⁸O and δD. Tell us about the local temperature when the snow formed.
Yes, stable water isotopes such as δ¹⁸O and δD are commonly used as temperature proxies, though they also reflect precipitation source and seasonality. You have to combine them with other evidence like borehole thermometry or gas isotopes to get robust temperature reconstructions.
What about synchronizing records between Greenland and Antarctica? How do scientists align the timing of events between hemispheres?
Scientists use several synchronization methods. Volcanic ash layers, or tephra, are excellent isochronous markers because a major eruption deposits ash over wide areas that can be geochemically fingerprinted. You can also use abrupt changes in methane, which is well mixed in the atmosphere. So rapid methane shifts appear in both Greenland and Antarctic cores and can be used as tie points.
I read about Dansgaard-Oeschger events in Greenland and bipolar seesaw patterns. Do ice cores provide evidence for interhemispheric climate leads and lags?
Absolutely. Ice cores show that rapid warming events in Greenland often coincide with more gradual changes in Antarctic cores. The bipolar seesaw idea comes from comparing the timing and magnitude of isotope changes and greenhouse gas records. After accounting for gas age, ice age differences, synchronization has shown that some Antarctic changes lag Greenland by centuries, suggesting ocean heat redistribution.
Are there specific case studies I should cite in my introduction that demonstrate these points clearly?
Yes, cite the original Vostok CO2 and temperature work that linked CO2 to glacial cycles. Cite Epicodome C for the 800,000-year CO2 record and the bipolar comparisons, and definitely include the Laudome high-resolution CO2 study that documents the industrial era rise. Also use GIS-P2 or NGR-IP studies for Greenland abrupt events and methane synchronization.
When you suggest using methane synchronization, is that because methane changes are global and appear simultaneously in trapped gases?
Yes, methane is relatively well mixed and responds to changes in wetland sources and biomass burning. It tends to show rapid shifts that can be correlated between cores, making it a useful stratigraphic tool.
What about measurement uncertainty? How do I present uncertainties in gas age estimates and concentration measurements?
You should include analytical uncertainties from the instruments, often a fraction of a part per million for CO2 and percent for isotopic ratios. Then include dating uncertainties from layer counting or modeled age-depth relationships. For deep Antarctic cores, chronological uncertainty can increase to centuries, so present those clearly and propagate them into any lead-lag analysis.
I plan to compare timing of CO2 rises and temperature proxies to infer leads or lags. Do I need to correct isotopic records for diffusion within the firn or ice?
Diffusion smooths high-frequency signals, particularly in firn and the top meters of ice. You should account for diffusion when interpreting short-term events. Use deconvolution methods if you want to recover higher frequency variability, but be cautious about amplifying noise.
This is really helpful. It seems I need to carefully choose cores and document resolution age offsets and analytical methods in my methods section.
Exactly. Lay out which cores you use, why you chose them, their temporal coverage, and how you handle gas age, ice age differences. Synchronization methods and uncertainty estimates will make your comparisons credible.
One last thing. Should I include raw data plots of CO2 and δ11O at depth, or convert everything to age first?
Convert to age for the main comparisons, but include a supplementary figure of depth profiles. Most readers want to see age-aligned records because that is where you infer leads and lags.
Thanks, Dr. Thompson. I will start drafting my methods with those points and bring a first version next week.
Good plan. I look forward to it, and check those case studies I mentioned for specific figures you can digitize for your comparisons.
Listen again to part of the conversation. Then answer the question.
Look at the law dome cores. They give annual to sub-annual resolution for the last millennium and show the sharp industrial CO2 rise.
This concludes the conversation portion. For more TOEFL practice tests and study materials, visit Spinta.org.